In the previous few lectures, we have discussed the theory of forced harmonic oscillation in very detail. Actually, you have seen what is this forced harmonic oscillator, what is its equation of motion, and how we can solve the equation of motion of forced harmonic oscillation. Okay? And during that discussion, we have actually found the amplitude of forced harmonic oscillator. And I have told you earlier that this amplitude of forced harmonic oscillation depends on two factors. The first one is the frequency of the applied periodic force. This actually determines the amplitude of forced harmonic oscillator. And at the same time, the amplitude of forced harmonic oscillator also depends on the damping coefficient, that is the resistive constant of the medium. You have learned about the expression for amplitude of forced harmonic oscillator. Actually, in this present lecture too, we will see that expression. But before this lecture, I have already discussed the expression for amplitude of forced harmonic oscillator. I am just showing you that expression which we have learned earlier in our previous lecture. This is the expression for the amplitude A of the forced damped harmonic oscillator. And you can see this A, which represents the amplitude of forced harmonic oscillator, that depends on two factors. This omega, which is actually the frequency of the applied periodic force or driving force, and B is the damping coefficient. Okay? And omega naught, you know, this is the natural frequency of the oscillator. So the factors affecting the value of amplitude of a forced harmonic oscillator are omega, which is actually the frequency of the applied driving force under which the forced oscillation takes place, and B, which is called the damping coefficient. Okay? So it is obvious that for a given value of B, that is for a given value of damping coefficient, there will be a particular value of omega, that is the frequency of the applied periodic force or the driving force, for which the amplitude of the harmonic oscillator is maximum. Actually, when the amplitude of harmonic oscillator is maximum, we simply say that there is a phenomenon known as amplitude resonance. It means amplitude resonance takes place for a particular value of the frequency of driving force for a given value of damping coefficient. And our aim in this lecture is to discuss this amplitude resonance actually. This is actually a very important phenomenon. It is of great importance in physics of oscillation. So whenever you talk about the forced oscillation, definitely you have to deal with the problem of amplitude resonance. Okay? This idea is equally important for your examination purpose of examinations of different categories, different types. That may be a university examination, that may be a competitive examination. This concept is equally important for all those competitive examinations and university examinations. So watch this video seriously and you will get a complete idea, a complete concept of this amplitude resonance in this lecture and few subsequent further lectures. Okay? The complete idea of sharpness of resonance will be discussed actually in the next lecture. But here we will also see a short discussion on sharpness of amplitude resonance too. Okay? So what is this amplitude resonance, when it takes place? All these things will be dealt in this video. Okay? And as I have told you, and you have seen the expression for amplitude of harmonic oscillation, that forced harmonic oscillation, that the amplitude depends on omega and B, and so that for a given value of B, there will be a particular value of omega for which the amplitude of the forced oscillator is maximum. And when the amplitude is maximum, it is said that amplitude resonance is taking place. In fact, you will see in our mathematical calculation that when the amplitude of the applied periodic force or the applied driving force under which the forced oscillation takes place will be maximum when the frequency of the applied force is equal to a square root of omega naught square minus 2b square. This is the value of the frequency of the applied driving force for which you will see later on the amplitude of oscillation will be maximum, and we say that amplitude resonance is taking place. So this very frequency omega r, which is equal to a square root of omega naught square minus 2b square, this is actually known as a resonant frequency. This is called a resonant frequency. And as you can see from here, since omega r is a square root of omega naught square minus 2b square, but b is very small, and so this omega r is slightly less than the natural frequency of the oscillator. In general, omega r, which is called resonant frequency, this resonant frequency is slightly less than omega naught square. But in extreme condition, if you consider that this damping coefficient is almost zero, or you may say that this damping coefficient is tending towards zero, in that very condition, this omega r is simply equal to omega naught. So this is the necessary and sufficient condition for amplitude resonance. So you can say that when the frequency of the applied driving force under which our oscillator performs the forced harmonic oscillation is equal to its natural frequency omega naught, then amplitude resonance takes place. So this is the necessary and sufficient condition for amplitude resonance. But how you can say that amplitude of the oscillator will be maximum for the frequency equal to a square root of omega naught square minus 2b square, or this omega r is almost equal to omega naught? How you can say? It means now our aim is to find this condition mathematically. I have mentioned this condition here directly, but now we will see the proof of this condition for amplitude resonance. So in nutshell, first of all, I would like to summarize what I have told you just now, that amplitude resonance takes place when amplitude of vibration of the forced oscillator is maximum. And when it will be maximum? It will be maximum only when the frequency of the applied driving force is equal to a square root of omega naught square minus 2b square. Okay? And so that this very frequency omega r is called resonant frequency, because resonance takes place at this frequency of the driving force. But actually in practice, this b is very small in comparison to omega naught, and so that we simply say that this resonant frequency is almost equal to the natural frequency omega naught of our oscillator. And this is actually a general fact, natural fact you can say. Let us see a practical example. If you are governed by a teacher, you are a student and a teacher teaches you, guided you, when you learn more, if the frequency of the teacher matches with your frequency of learning. The frequency of teaching of the teacher and frequency of learning of the student, when matches, then gain is maximum. Students learn more and more. And so you can say then resonance takes place. But if the frequency of teaching of your teacher is very different from your frequency of learning, you do not learn much more from your teacher. You simply say that I am not getting the things, I do not understand what my teacher taught. Okay? So it is a natural fact when the driving force has a frequency which resembles, which is almost equal to the frequency of the natural frequency of the oscillator, then amplitude is maximum, and it is said that amplitude resonance is taking place. Okay? So this is the necessary and sufficient condition for amplitude resonance to be taken place. Okay? But now we will see how you can say that when omega r is equal to root over omega naught square minus 2b square, or omega r is almost equal to omega naught, then amplitude of oscillation will be maximum. Now let us see the proof. Okay? So in this mathematical analysis, we are going to prove this fact. Okay? And for this, you have to think what you have learned in my previous lecture. You can remember, I have considered in my previous lecture that when the driving force is taken in this form, F equal to F naught cos of omega t, then what is the displacement of our oscillator? You can remember, actually this result which I have written here directly, I have already derived in my previous lecture. So when you consider that driving force is equal to F naught cos omega t, then you have seen earlier that displacement of the oscillator at any time t, which is given by x of t, is given by F naught over omega times Zm times sine omega t minus phi. Okay? And instead of this F naught over omega Zm, we simply write A, and this A is nothing, this is simply the amplitude of the forced harmonic oscillator. And you know, this Zm, which is actually called the mechanical impedance, complex mechanical impedance. Omega is the frequency of the applied force, and F naught is the maximum value of the driving force. Okay? And this phi represents the phase constant. Okay? So what will be this A? A is equal to F naught over omega times Zm. Okay? And we have also learnt earlier that this Zm is equal to what? In this phasor diagram or vector diagram, you can represent this R, which is resistive constant, on the real axis. This is your real axis. And this m omega minus k by omega, this is represented on the imaginary axis. This J operator simply represents a rotation of 90 degree. So this m omega minus k by omega is rotated by 90 degree with respect to r. And from this vector triangle, you simply say that this r plus j times omega m minus k by omega, this is equal to the complex mechanical impedance Zm. I have written here Zm in vector form, as we have written earlier too, because any complex quantity is just equivalent to a vector. Okay? And this phi represents its argument or its phase constant, you can say. Okay? And so, as Zm vector is equal to r plus j m omega minus k by omega, j you know this is iota, j means what? J is a square root of minus 1. This is iota. I have not written I here, I have written j. Okay? But you can write it I too. So, Zm, this is modulus of this vector Zm, and that will be equal to a square root of r square plus m omega minus k by omega whole square. All these things we have discussed in very detail in our previous lectures. Okay, and you also know that this 2b has been written at the place of r by m, where r is called resistive constant, and so r is equal to 2bm. Okay, and omega naught, which is the natural frequency of our oscillator, its a square omega naught is a square is given by k by m, and so that k can be written as m omega naught square. Okay, so in this expression for modulus of Zm, now replace this r by 2bm and this k by m omega naught square. We replace it, and so that expression for Zm now becomes like this. This is square root of 4m square b square plus m omega minus m omega naught square by omega whole square. Here m omega naught square has been written at the place of k. Okay. Now let us take LCM here. When you will take LCM, you can see this will be 4m square b square plus m omega square minus m omega naught square over omega. We will again take the LCM, and after taking LCM, here there will be actually what? There will be 4m square b square omega square. Okay, and plus m omega square minus m omega naught square whole square, and whole divided by omega square, and whole to the power half. Okay. Now you can see in numerator we can take this m square as a common factor. Okay, and in denominator there is omega square, and these two quantities are inside the square root. So when we will take it outside of the square root, our expression for Zm now becomes like this. This will be m over omega times a square root of 4b square omega square plus omega square minus omega naught square. You can see, because I have taken this m square as a common factor, here also m square will be common factor. Okay. So this is the expression for the modulus of the mechanical impedance. Okay. Now you have seen that amplitude of this oscillator is given by f naught over omega times Zm. Okay. Now let us substitute the value of this Zm here. So what will be this? This will be f naught by omega, and 1 over Zm. 1 over Zm, that will be equal to omega by m times 1 over a square root of 4b square omega square plus omega square minus omega naught square whole square. Now you can see this omega will cancel out, and f naught divided by m, capital F naught divided by m, this is written as a small f naught. This has actually the dimension of acceleration. Okay. So the expression for amplitude A now becomes like this. This is small f naught, which has been written at the place of capital F naught by m, and divided by a square root of 4b square omega square plus omega square minus omega naught square whole square. Okay. This is the expression for amplitude of the forced harmonic oscillation. Okay. And you can see, as I have told you in the beginning of my lecture, that this amplitude A depends on omega, which is frequency of the driving force, and B, which is the damping coefficient. Okay, damping coefficient. So definitely when omega will be varied for a given value of B, amplitude A will also vary. And for a particular value of omega, this A will be maximum. And when A is maximum, we say that amplitude resonance is taking place. Okay? Now we have to see when A will be maximum. For what value of omega this A will be maximum. Okay? As you can see, since this small f naught is a constant factor, so A will be maximum only when the quantity in the denominator will be minimum. Because when we will divide f naught by the minimum value of denominator, then we will get the maximum value. Okay? So you can say that this amplitude A is A max. It means it is maximum when a square root of 4b square omega square plus omega square minus omega naught square whole square to the power half is minimum. Okay? And since this will be minimum, so you can also say that when we do not take the square root, but we take simply 4b square omega square plus omega square minus omega naught square whole square, when this will be minimum, then this will be minimum and A will be maximum. But you know from calculus that this quantity or this function, which is a function of omega, if it is minimum, then its first order derivative with respect to omega will be definitely 0. This is the first theorem on maxima and minima. Okay? As this quantity 4b square omega square plus omega square minus omega naught square whole square, this is a function of omega for a given value of b. So if this quantity will be minimum, you know from calculus that its first order derivative with respect to omega will be 0. So let us write this condition. You can see I have written d omega operated on 4b square omega square plus omega square minus omega naught square whole square. This is equal to 0. Now let us simplify this. You can see 4b square is a constant factor and derivative of this omega square will be 2 omega. Okay? Now we will differentiate this omega square minus omega naught square whole square. Actually, this is a function of function. First of all, this will be differentiated with respect to omega square minus omega naught square. And that will be 2 times omega square minus omega naught square. Now, this omega square minus omega naught square will be differentiated. You know, derivative of this omega square will be 2 omega, and since omega naught square is constant, so its derivative will be 0, so that I have not written it here. So your result is 4b square times 2 omega plus 2 times omega square minus omega naught square times 2 omega is equal to 0. Now you can take this 4 omega as a common factor, you can see. So our result will be 4 omega times 2b square plus omega square minus omega naught square equal to 0. Now, as this omega is not 0 because this is the frequency of the applied periodic force, and so definitely this second factor inside this square bracket will be 0. So we can write 2b square plus omega square minus omega naught square is equal to 0. And from here you can see this omega square will be equal to omega naught square minus 2b square. And so omega is equal to a square root of omega naught square minus 2b square. And so in this way we have obtained the value of omega, which is the frequency of applied driving force for which amplitude A will be maximum. Or in other words, you can also say that this is the frequency of the applied force for which amplitude resonance will take place. Okay, and that's why this particular frequency defined in this equation 3 is called the resonant frequency, and we will denote it by the symbol omega r. Okay. So you can see it here. This omega r, which is called resonant frequency, this is given by a square root of omega naught square minus 2b square. And as you can see from this result, since this b square is much smaller than omega naught square, so omega r is slightly less than omega naught square. I have written here omega r is less than omega naught. So in fact, in case of the resonance, the frequency of the applied driving force will be slightly less than the natural frequency of the oscillator in practice. But if you consider an extreme condition, that is the condition of no damping, there is no damping, and in case of no damping, this damping coefficient will be 0. And in that very condition, you can see from here that this resonant frequency omega r will be equal to the natural frequency of the oscillator. So this is actually the condition for amplitude resonance. Amplitude resonance actually takes place when the frequency of the applied force is almost equal to the natural frequency of the oscillator. And this fact I have already stated earlier, but now you have proved this very important fact. Okay. So what is the frequency at which amplitude resonance takes place? And amplitude is maximum. You can see this is the value of frequency omega of the applied force for which the resonance takes place, or amplitude of the oscillator is maximum. So now if our aim is to find the maximum value of the amplitude, how we can find it? We can easily find it simply substituting that value of omega in this general expression for the amplitude. Equation 2 defines the general value of amplitude, and when you will substitute that particular value of omega in this equation 2, you will get the maximum value of amplitude. So here I have substituted the value of omega equal to a square root of omega naught square minus 2b square in that very equation. And so you can see A max will be equal to F naught divided by, in denominator there was 4b square omega square. But now at the place of omega square, what we will write? We will write omega naught square minus 2b square. And plus there was omega square minus omega naught square. So again, instead of omega square, I have written here omega naught square minus 2b square. Okay. Now let us simplify this equation. Okay. You can see A max will be equal to what? You can see the denominator. This is 4b square omega naught square minus 8b4. This is the first term. 4b square omega naught square minus 8b4. Okay. And here this omega naught square and this omega naught square will cancel out, and there will be minus 2b square, and that will be 4 plus 4b square. So here there is plus 4b square. Okay. Now 4b, not 4b square but 4b4. Now 4b4 minus 8b4, that will be minus 4b4. Okay, so A max is equal to a small f naught divided by a square root of 4b square minus omega naught square minus 4b4. Okay, and now you can take this 4b square as a common factor in denominator, since it is inside the square root. So when you will write it outside of the square root, you have to write 2b. So A max will be equal to a small f naught divided by 2b times a square root of omega naught square minus b square. Okay, and this is the maximum value of amplitude of the forced harmonic oscillator, and this value of amplitude is possible when resonance takes place, when the frequency of the oscillator is same as when the natural frequency of the oscillator is same, almost same, not same, of the applied periodic force. Okay, but if now again we consider the extreme condition of no damping, that is B equal to 0, you can see from this equation 4 what will be this A max. When B will be 0, you can see there will be A max will be simply equal to F naught divided by 0, because 0 times something will be 0, and when you will divide a non-zero by 0, your result will be undefined. So in this condition, case of no damping, A max tends towards infinity. Okay, but when B is not 0 but small, then A max is equal to a small f naught divided by 2b times a square root of omega naught square minus b square. So when resonance will take place, what is the maximum value of amplitude during the resonance, all these things is now clear to you. You can see resonance takes place when the frequency of the applied force is equal to this much, a square root of omega naught square minus 2b square. And in extreme condition, it is simply equal to omega naught when the damping coefficient we take 0. And in this condition, amplitude of oscillation is maximum, and that maximum value is defined in this equation 4, that is A max is equal to a small f naught divided by 2b times a square root of omega naught square minus b square. And again, if we consider the extreme condition of no damping, that is when we take b equal to 0, then you can see that this maximum amplitude tends towards infinity. Okay. Now we will see in very shortcut the concept of sharpness of resonance. Although we will again discuss this problem of sharpness of resonance in terms of bandwidth and in terms of quality factor in my forthcoming lecture. But here, for your examination purpose, let us see if a question is asked, discuss the theory of damped harmonic oscillator and what is amplitude resonance and discuss its sharpness. Then you can write the answer which has been written in this video. But if there is a question, what is amplitude resonance, and discuss in detail the sharpness of resonance, only this question is asked, not the basic theory of forced harmonic oscillation, then we will have to discuss this sharpness of resonance in terms of the bandwidth and in terms of quality factor, which we will see in my forthcoming lecture. Okay. But here, what is this sharpness of resonance? When resonance will be called sharper, we will see it here. Actually, you have seen that amplitude of resonance A, which is given by this expression, F naught divided by 4b square omega square plus omega square minus omega naught square whole square to the power half. And you have just seen that this amplitude A is maximum, that is A is equal to A max, when the value of omega is equal to this much. This is a square root of omega naught square minus 2b square. And when we take this b very small, negligibly small in comparison to omega naught, then this omega is simply equal to omega naught. And you know this is the condition for amplitude resonance. So we can simply say that when the frequency of the applied driving force is equal to the natural frequency of our oscillator, amplitude resonance takes place. Okay? And so in condition of amplitude resonance, if you take omega equal to omega naught, what will be this amplitude? For this, we will substitute omega naught at the place of this omega. Okay? And then this omega square minus omega naught square, that will become 0. And so A will be then simply equal to this much. This is F naught divided by 2b omega. Or you may also write here omega naught, because in this condition omega is equal to omega naught. Omega is equal to omega naught. And this is actually the maximum value of amplitude. And so you can see from here that when this omega will be equal to omega naught, then A is maximum. Okay? But when omega deviates from omega naught, it means the value of omega is either greater than omega naught or less than omega naught, this amplitude will fall. Amplitude will decrease. So a deviation from omega naught, that is deviation from the resonant frequency of the frequency of applied force, amplitude certainly decreases. Okay? Certainly decreases. As you can see in this figure, I have shown a graphical plot of amplitude of oscillator in against of this omega. Okay? And for different value of the damping coefficient. When you take damping coefficient is very large. In this figure you can see I have taken here B is large. When B will be large, you can see that this A will have not a large value, but A will have a smaller value, because B is in denominator. Okay? And when omega will be omega naught, A will be maximum. Okay? And the variation of this A with omega is shown by this first curve. So this first curve represents the variation of A with omega when B is large. And you can see the peak value here is at omega equal to omega naught. And when the omega is increases from this omega naught, you can see that amplitude decreases. When omega is smaller than omega naught, again this amplitude decreases. Okay? And when omega is equal to omega naught, then A is maximum. Okay? But this second curve represents the variation of A with omega when B is not large but B is small. And you can see in this condition the resonance is sharper. There is a sharp maxima. Actually, when B is large, there is a flat maxima, and when B is small, then there is a sharp maxima. But when B is 0, it means damping coefficient is completely 0, then you can see that this A tends towards infinity. A is tending towards infinity. Okay? Now, when you can say that resonance is sharp, or when you can say that resonance is flat. Actually, you can see when the frequency of the applied force slightly deviates from the resonant frequency omega naught, and due to a small deviation of omega from omega naught, if there is a large fall in the amplitude, then resonance is called sharper. Okay, are you getting the things? For example, let us see here, there are two curves here. Okay, and I have actually drawn here the another curve. Now see, if we consider that this is omega equal to omega naught, okay, and we take a point which for which omega is slightly different from omega naught. So let us draw a line here. You can see the amplitude at this point and amplitude at this point does not differ from one another more, but corresponding to the same omega, amplitude at this point and amplitude at this point differs large. So you can see in second figure, for a slight deviation of omega from omega naught, there is a large fall in amplitude. But in the first figure, due to that a small or slight deviation of omega from omega naught, there is not an appreciable fall in the amplitude. So in this condition, resonance is called flat, but in this second condition, resonance is called sharp. So condition for sharpness of resonance is what? When we deviate the frequency of the applied force from the resonant frequency omega naught slightly, but due to a small change in frequency, there is a large decrement, there is a large fall in the amplitude of the oscillator. Then we say that resonance is sharper. Okay, I think we have understand when resonance is called sharp. Actually, I have written it here. You can see, as the value of frequency of the applied force omega is increased or decreased from its resonant value omega naught, the value of amplitude always decreases. Either you increase omega or you decrease omega from omega naught, amplitude will decrease. Okay. Now, if due to a slight deviation of omega from omega naught, there is a large fall in amplitude, then resonance is said to be sharper, otherwise flat. But if the phenomenon is not like that, then you can say that resonance is flat, not sharper. Okay? And you can see that from that figure, when the damping coefficient B is large, resonance is flat. But for a smaller value of B, resonance is sharper. And in extreme condition, when B tends to 0, then resonance is very, very sharper, or we simply say that in that very condition, the maximum amplitude tends towards infinity. Okay. So this was all about the amplitude resonance of a forced harmonic oscillator. Okay. But this problem of resonance is not completed in this lecture. Actually, in forthcoming 2 lectures, we will again see this problem. As I have told you earlier, we will discuss this sharpness of resonance in terms of a very important parameter which is called quality factor in our forthcoming lecture. But before that, we will have to discuss the power supplied by the driving force to the oscillator. What compensating power it supplies to the oscillator to maintain its oscillation, we will see in our forthcoming lecture. Okay, I think you have definitely understand this lecture clearly. So I will again suggest you write down all these things in your notebook, because that will be a very good assignment for you. Okay, thank you very much.